Okay, so let me bring back some problems and some activities we've done in the past right here. Let's say when we were doing this, the idea originally came out from solving an equation, say sine of theta, right, equals to a 1/2, for example. Okay. We've done things like this, like solving a trig equation, and then we want to solve that for, we want to solve this equation here for theta. Right? So now if you look back in what we've learned throughout at least your time with me and in my teaching style right here, I've been showing you that, hey, when we're doing this, right, we got this equation right in the fundamental form, right, and then we just now going to search through the unit circle. You see what I'm saying? Yeah? Okay, and so our answer here, and let's say we start out with on the unit circle, we start out with the basic period, so that gives me theta. We found theta to be there are two values, right? So one of them is to be a pi over 6, right? And there's a 5 over 6. See what I mean? And then from there we built, a lot of solutions, right? Because we've got many other points at coterminal with pi over 6 and many other points at coterminal with the pi over 6. You guys all agree with me on that? Okay? So the main idea we did this, the main method that we used to handle this problem right here was just simply to look around the unit circle. Okay? But then think about it. The idea is there, the idea about solving a trig equation, you got sine of theta, right? A trig function of an angle, we want that to equal a specific value or cosine theta. Right? This is what we did. The fundamental equations are still here. We want cosine theta equals some k value or tangent of theta, right? Equals some k values. These are all the fundamental ones, and I kind of diminished the importance of secant and cotangent and cosecant because they all came out from this thing. But in the end, let me now point out for you. So the only methods we know and we relied to was looking through the unit circle, right? Now, what if I'm asking for something like this? I want you to solve again, right? It's a very similar task. We want to solve sine of theta, right? But instead of 1/2, let's say I'm going to go with 0.7. See what I mean? So, well, if we stick with the traditional methods, well, we want to solve that for theta. So now if we use this unit circle over here, this is where it's making it harder for us because the unit circle has reached its limitation. Because, on the unit circle, where on that unit circle gives me a sine being a 0.7. Are you understanding what I'm trying to point out right now? Sine being a 1/2. Again, sine is a vertical, as your terminal point on the circle, right? Your terminal point is on the circle. So sine value is the y value. And so sine value being a 1/2, we can easily calculate that the angle here is a pi over 6. Agree with me on that, okay? But now the sine value, we think about we at the different terminal points. The sine value is a 0.7. That point right there. X for cosine, 0.7 for y, which is the sine value. But what angle is that? Do you have, can you really find among those? I'm not saying that it's not there, but do you really know, does the unit circle really tell you what angle that is, that's giving you exactly a 0.7 for sine again? It doesn't, right? See what I'm saying now? And so, when it comes to that, now we need a special tool here. So the idea is, again, originally it came out in serving that purpose of solving a trig equation, sine or cosine of theta or tangent of theta equals a given value. Okay? And behind the scene, the work that we did, we're looking at it up on the unit circle right there, but really behind the scene, we formulated the idea as following. So the answer to this is whatever that comes out from, we're taking what's so-called the sine inverse. Okay? The sine inverse of 0.7. See what I'm saying? The word thing about the thought process, see when you were going from a 1/2 and trying to translate that back to the, hey, what angle gives me a 1/2 for sine, right? The thought process there is the process of taking the sine inverse. See what I'm saying? Okay, so this symbol right here, ladies and gentlemen, we call this symbol the sine with the superscript -1 right here. Okay. saying it out loud, we call it, it's a sine inverse. Sine inverse of this 0.7. But just that symbol itself means sine inverse. Or sometimes we call it, or equivalently we call it the inverse sine. So that's just general. The idea is we to find an angle, we take the inverse, right? We take the inverse of that sine value. So here, you're gonna label that for yourself. Here, the value we have here is sine value of the angle theta. Sine value of the angle theta. But it's just not that easy anymore to find it on the unit circle. See what I mean? It's not that easy anymore on the unit circle. So turn on the calculator. On your calculator, there should be a key somewhere that says sine with a superscript -1. But so then, before we run this command, let's say for now, why don't you turn your calculator into degrees mode right now? Okay, keep your calculator in degrees mode for now. And so, if you're using the standard TI calculator, like in the family of the TI right here, then you go, there's that button, right? The sine with the superscript -1, you hit that button. And then when you hit that button, it gives you sine with a -1 in a parentheses, okay, right on your screen. You guys following? Right? And then you put in a number. So here we're putting in a 0.7. That's the next step, right? So that means you put the 0.7 inside. Make sure to close the parentheses. You know what I'm saying? No? And then we hit enter. Okay? Go ahead and run that. Okay, see what you got. Okay? So who had the answer? So 44.43. Right? The answer that came out from your calculator gave me about 44.43. So rounding to 2 decimals, which is a very common practice right there. I'm not saying that it's a hard or strict requirement about how far to round, but the idea that you have at least some good imagination about how big that angle is. See what I'm saying? Okay? So now think about the impact for you. Let me bring that on the circle. Right now, this is our unit circle right there. Now, the pi/3 angle is about right here, which is easy to find, right? And then that point right there is see the y value here is a 0.5, which is also a 1/2. That's sine value, so that's easy, right? That we can just easily look it up on the unit circle. See, the next one easy on the unit circle is going to be the 45 degrees angle, which is about right there. So 45. I'm having a little bit of a hard time getting 45 exact. See, 45 right there on the unit circle. That one, the sine value comes out being the sine value for here. Okay. Now, if I click on decimal here, it shows a 0.707, so slightly more than what we've had, right? The one we had was a 0.7 exact. See what I'm saying? Now, this thing here in exact is a square root of 2/2, but our value that we did right there wasn't square root of 2/2. It's just a little bit less than square root of 2/2. So it's in between. My point out, it's in between the 45 degrees angle and the 30 degree angle right there, which is what makes it hard to find on the unit circle. And so now we define that operation. Okay, we define that operation that says we're taking that sine inverse. The calculator now is programmed to handle that calculation right there. So now it comes out for us. See, now it makes sense right here that the angle is 44.43 degrees. Not big enough, not as large as the 45 degrees, right? But bigger than the 30 degrees angle. See what I mean? Okay, and that's the idea of the inverse function right there. That's the major idea of the inverse function. Are you guys with me on that so far? Okay. And so in that way, we have already looked and investigated at the sine inverse. So we can also work the same way with the cosine inverse. At least these 3 fundamental trig functions right here, right? They all have a programmed trig inverse function going correspondingly right on your calculator right there. Okay. But anyway, see, we can once again back to that problem we've done all over. Solve the cosine of theta, right? We want cosine of theta to be a how about 1/2 right there. Okay. So we want to solve that for theta. See what I mean? So just by using the unit circle right here, that we can find theta equals what we got a pi over 3. That's one of them, right? And then we have another one here being a 5 pi over 3 degree. Right? That's just by easily looking it up on the unit circle over there. So we've done that, and then of course there's a whole family of those other co-terminal points that come out, right, from this, from these two easy values that we look it up again. But now think about, see, once again, if I'm asking, hey, if you find cosines, right? If you find, you want to solve cosine of theta, that equals to a 0.9, for example. Okay. This is where the challenge came. See what I'm saying now? Because something like this, right? Well, by the way, numerically speaking, 1/2 is a 0.5, right? So cosine, think about on your unit circle. We want to look for that terminal point, what angle that is, so that it gives me cosine right here, right? Being a 0.9. So being a 0.9 is actually a pretty big, because 1 is here on the unit circle, so 0.9 is slightly off, right? That distance right here is 0.9, see what I mean? So we want to find out, hey, what angle is that? Giving me 0.9 for cosine. Right? And cosine, recall for yourself, cosine is the x coordinates of your terminal points. X for cosine, and sine of theta is for y, right, on the unit circle. Got all that reminded? Okay. And so, so to answer this, really, we cannot do the mental math, and the unit circle is not helping anymore, right? But deep behind the scene, the process that we're doing, the brain process that we're doing here is that we were doing this. We want to check the inverse operation. See, the operation is sort of like a process, a something to do, right? Something that we do to a number, to a value right there. So we take the inverse cosine, right, of 0.9 right there. That's the way how we're writing it. You know what I mean? Right? And then the way how we understand about it. That's superscript -1, right there, cosine with a superscript -1. The way we're reading it, right? So we hear more people saying cosine inverse. That's one way. Right? Or a little bit less popular, people say inverse cosine. 2 different ways of saying that, but I don't know why more people say cosine inverse. And then cosine inverse of 0.9. Like that. Right? Or the inverse of the inverse cosine of 0.9. So now, really, what is the answer? We kind of know what it is. We kind of predict where it is. But in the end, in order to find the exact degrees, right? Let's go ahead and find out right there. So once again, I'm going to come back to this board. Keep your calculators in degrees right there. Run your calculator in degrees. And then what about we run? There should be a key on your calculator, as long as you're staying with the recommended calculator, right? There should be a key there that says a cosine with a superscript -1, right? So we call it as a cosine inverse, right? So cosine inverse, and then when you press that key right there, right, it's gonna print out cosine inverse with the parentheses on your screen, right? If we were staying with the standard TI calculator, and then the next thing is to type in the number. So 0.9 right there is the number you're putting in. So right at the parentheses, the opening parentheses right here, you put the 0.9 in there. And then of course we're going to close the parentheses and hit enter. Okay, that's how we're running it. There you go. So I hear 25.84 degrees right there. So we found in degrees right there. It's about 25 degrees. And so once again, let's see how it makes sense with our unit circle. And of course, we have to do this with the calculator, right? Now, again, let me do that demonstration right here for everyone. You see that? See right now, I'm indicating about 30 degrees right there on our screen, right? About 30 degrees on our screen right there. That terminal point on our circle, the coordinates for x, right? Which is also understood as the cosine value of theta is about 0.866, right? But see, exactly at 30 degrees angle, then this 0.866 right here is the square root of 3/2. You guys still recall that from our previous learning? But then that's not 0.9, right? So 0.9 means the angle is going to be a little bit lower, about somewhere there, right? And 0.5 comes to somewhere close enough. See what I'm saying? That it's a 0.906. Okay, that's you're seeing, right? And so in that case right here, that's how the answer is. It's somewhere near there, like the 25, and according to the work that your friend here gave me, right? It's 29.25, something like that, or 23. 25.84. 0.84. Okay. There you go. So it's a little bit bigger than 25, right? It's somewhere between 25 and 26 degrees again. Okay. All right. And so that's how we get an idea out of that, right? So now let's confirm our work here. So you have seen that. So I'm going to put it together with the earlier work that we've done. So now anytime that we're seeing, hey, people actually do the sine inverse of a value k, right? And whatever that answer comes out right there, it means you want to solve, right? You want to solve the equation sine of the angle theta that we're still looking for right there, because theta is the unknown one. See what I mean? It means we solve this angle theta, right? We solve this equation here for theta. It means like that. And then the same way right here, the cosine inverse operation that we've done, right? You guys just pushed in a calculator right there. And supposedly it comes down to some theta value, right, that we're looking for, right? But it means the same thing as it means that we solve the equation cosine of theta. We want that cosine of theta to equal some specific given k value. So now, let's compare answers. Now take careful note here. I'm going to roll back to this earlier problem when I promoted. Hey, when we solve the sine of theta, right, to equal 1/2 here. Theta, if we were doing this using the unit circle, we come out with these answers here. One of them was pi over 6, right? And the other one was a 5 pi over 6. Once again, we'll double check it there, see if you guys agree. So with the unit circle, we came out with two answers, right? So now, staying with this equation right here, just now I explained it in the way I explained it there. And solving this equation means the same as we're taking sine inverse of what? Sine inverse of 1/2 here. See what I mean? To find like I said, the sine inverse here is more like a thought process. Like, hey, we want to find out what angle that is, right? What angle that is giving me sine value here to 1/2 here. Okay? So keep your calculator in degree right here and run that. Let's run that in degrees again. Let's run sine inverse of 1/2. For your calculator, you can type in 0.5 again, right? Sine inverse of 0.5. What kind of answer you have? Okay. Okay. Take a little bit of time doing that. 30, right? 30 degrees. Now, let me ask one more question. Hopefully it's not too much. How many answers did this give you? How many answers did your calculator give you? One. I thought we even have two answers, right? 1 to 30 degrees here agrees with this. 5 or 6. You guys follow? And this 5 or 6 here is about what? 150 degrees, right? But the calculator, after running the sine inverse, didn't give out two answers. It only gave out 30 degrees. See what I mean? Right? And 30 degrees here, yes. If you think in radians, it's a pi over 6 angle. So the truth now is that, hey, inverse trig function has a certain restriction, okay? A certain restriction right there. It's not like it gives you, so still, at some point, if you know the unit circle is still bad, right? But anytime that you have to use the inverse function, you got to be aware of something that's, so, again, inverse trig of any value, right, equals to, the aim, the purpose is to come out with the angle. See what I'm saying now? So you need to label that, and so do x. This is, when you take inverse trig of the sum, the number here is the sine value, right? And then the outcome right here, the final value right here is the angle. That's why we label it theta. But now, something just open up our understanding a little bit more in terms of this discovery right here that anytime you run inverse trig operation, right? The trig, the sine inverse operation. Anytime you run the sine inverse operation, the answer here only come out. The answer only come out for any theta that falls anywhere from minus pi over 2, pi over 2. You only have answers in this zone only. Right? Or in another way of saying, you only come out with angles anywhere from minus 90 degrees to 90 degrees. And so what it means here's that. When you run through your calculator, the inverse sine here, the inverse sines only give you an angle that says anywhere in quadrant 1 and quadrant 4 only. See, these two quadrants we count as negative pi over 2, the pi over 2 angle here. You only say your angle can only come out anywhere in that region. That's why it has a little bit of disagreement. It had a little bit of disagreement with our work, and we looked on the unit circle. The unit circle, we were able to go through the whole circle, right? But here, we can only give us the answer that stays in either the first quadrant or the fourth quadrant. And then to illustrate the idea one more time, let me bring in another thought right here, and it will get so clear for you guys. Right? So keep in mind, I just now talked about, hey, running a sine inverse operation, right? Our purpose is to come out with an angle value, with a known sine value. That's why we're taking sine inverse. We're going back, we go to the opposite process, right? Having a known sine value, we go back to the angle. And then the angle can only come out as a convention, as a restriction. We only come out for an angle anywhere from minus pi over 2 to pi over 2. So think about this equation. Sine of theta equals negative 1/2 right here. Okay? With the unit circle, this is what we have, what we see right here. See, don't we go with so minus 1/2 gives me a 7 pi over 6. That's one answer, right? We did a 2 pi standard period treatment. And then another one, we did a 11 pi over 6. We on that again. So, and by the way, as a degrees right here, this means 210 degrees, right? Another 30 degrees away from 180, right? And then this one right here is 330 degrees, right? But it's also the co-terminal with, because think about unit circle over here. That point down there, right? 330 degrees. But you can also think of that as in terms of a negative rotation. So, positive 330 degrees or positive 11 pi over 6. It's the same. It's co-terminal with a minus pi over 6 in radians. You guys agree? Okay. Co-terminal, same point. If you go positive, that lands at 11 pi over 6. But now if you're taking that as a negative rotation, you go down that way, it's only rotating negative 30 degrees away. So minus 30 degrees or a minus pi over 6. Okay. So something for you to be aware. And then same way right here. This 210, right? It's the same as a negative rotation. It's the same as minus 150 degrees. Okay? And then it's the same as minus 5 pi over 6. So now that's how we found these answers, and we've got different ways of interpreting it, right? We've got different interpretations of the same angle on the unit circle. So let's try to get that answer from the calculator point of view by using the calculator. And again, I'm in the middle of really getting it clear for you guys about anytime you're running a sine inverse operation, okay, then you're going to come out with an angle that's only, it's just the way how we purposely design it. The angle theta being in that interval anywhere from minus pi over 2 to pi over 2, okay? Or minus 90 degrees to positive 90 degrees. So let's investigate this. Let's discover this. Sine inverse of negative 0.5. That's the way how it is for being a negative 1/2, right? Go ahead and run it. What kind of answer you guys got? keep your calculation in degrees again. Let's keep our calculation in degrees. Negative 30 degrees. That's the answer that come out. By the way, before I go further into this, how many answers did that give you guys? Or one. See, so a little bit contradicting with, and it's not really, I don't see that as a contradiction, but it's just a little bit different from the way we did that on the unit circle. Then, well, if we're doing this, see, sine inverse of a negative value, right? Or we solve this equation for a negative value right there, then on the unit circle with a standard period, then we go with 7 pi over 6 and 11 pi over 6 and all that. And we can always think of those as a negative angle because in terms of a negative rotation, right? But then as far as answer, using the unit circle, we always going to end up with 2 answers. But now the calculation here only comes out with minus 30. Only one answer. Now do you see why that is? Between the 2 answers, it hit this guy, negative 30. Why? Yes?
Because of the restrictions.
Because of the restriction. The program, I mean, think about it. This feature right here on your calculator, it was programmed by whoever the engineer, the programmer who designed it, right? And we agree worldwide that the outcome from a sine inverse function only come out under this restriction right there. See what I mean? That's why you cannot violate the way how the world has accepted it, right? And so they programmed. So that's why the answer here comes out only being that this minus 30 degrees falls right in that interval, in that interval, whereas minus 150 degrees was way out in that interval. Right? So in that way, yes, we got some good enough in-depth look at the sine inverse. So what about the cosine? We have cosine theta. We want to solve this, including cosine of theta that equals a positive 1/2, right? We've done this earlier, right? And then using the unit circle. And notice that the number on the right-hand side here is a positive. We want a positive cosine. Anyway, so using the unit circle, we came out with 2 answers. Pi over 3, that's one of them, right? And a 5 of pi over 3. All agree with my work so far? And then, of course, in degrees, because these answers are more commonly in the radians, right? But in degrees, these are what? This is a 30 degrees, no, 60 degrees, right? And this is a 300 degrees. But using the unit circle, we came out with 2 answers. That's one thing for sure, right? Using the unit circle. So why don't you apply that process with using the process here is you go from a known cosine value and you want to find out what angle it is, right? What angle it is. So why don't we fire up the cosine inverse operation? We go cosine inverse of 0.5, right? Let's see what kind of answer we got here. 60 degrees. Right? How many answers did it give you? Just one. So among the 2 answers that we found through the unit circle, this function from the calculator only came out, right? This operation on the calculator only came out with that one as a choice. You want to say it, huh? So once again, let me point out for everyone in general, the cosine inverse also comes designed, right, with a restriction. So when you run cosine inverse of a known cosine value, and hopefully you come out with some angle theta, then the angle theta here is restricted. As a worldwide convention, it's restricted. And later on, I'm going to explain the reason why they chose that restriction. It's more like a chosen restriction like that. And we will understand why they chose that. But it runs anywhere from 0 to pi, the angle that comes out. Anywhere from 0 to pi. Or from 0 to 180 degrees. Right, degrees. And that explains why, technically, if we were using the unit circle, there were 2 answers, right? One of them being the 60 degrees, the other one being the 300 degrees. But now, if we run the cosine inverse operation on our calculator, the calculator only knows to give us that answer that falls into the restriction that the answer here is 60 degrees. Yeah, 5 3, right? That falls right in inside of this required interval. Okay. See that? Alright, so now at this point right here, you guys are ready for me to give out that definition here. So let's come to a formal definition. What it means by being a sine inverse or cosine inverse. So these are a few definitions we want to come up with. Now we're talking about for the angle, right? For the angle being restricted to anywhere from minus pi over 2, pi over 2. Right? For those angles being restricted between pi over 2 and minus pi over 2 and pi over 2, or think of that as a minus 90 degrees to 90 degrees right there, then sine inverse, right, of a value k will equal the angle theta, right? If and only if. Another way of saying if and only if is sort of like whenever sine of theta equals k. That's what I was explaining earlier on this board, on that other board earlier about any time that we're taking cosine or sine inverse, right? An inverse trig function. You think about that as solving the trig equation. That's why there are such equivalents like that. See, taking sine inverse of a value is the same as solving that equation for theta. You know what I'm saying? That's another way of interpreting it, but formally writing it down as a definition. That's how we're writing it. Sine inverse of a number right there. If that value comes out being a value theta, that means taking sine of theta equals k. Right? And so we're going to do the same here. So that's one definition for what it means by being a sine inverse. So now we have, and then before I write down the next one, so you see, anytime you take the sine inverse, it comes with a restriction, right? And that's the restriction I've been talking about before we get into writing down the formal definition. And so now further, for angles that's restricted to the interval anywhere from 0 to pi, right? Then we define the cosine inverse operation. So cosine inverse of a value k right here must coming out being an angle theta means the same, or if and only if. So many ways of saying this. If and only if, or it means the same as cosine of theta equals k. Okay. Have another definition of that. And then we didn't get to do any of these yet, but I briefly talked about tangent inverse as well. So just like that, right? For angle theta restricted in the interval anywhere from minus pi over 2, indeed, strictly between, not even including these, because when we got to minus pi over 2 and pi over 2, we got an undefined tangent. So for any angle strictly between minus pi over 2 and pi over 2, we define that the tangent inverse of a value k means, or that tangent inverse value coming out in an angle theta means the same as, that's what the if and only if means. It means the same as taking tangent of theta will equal k. Okay, so that's just the basic, the fundamental definition. So now you got to keep in mind again a couple of things. So everything that you've learned from before connects closely with what we're doing now. And that's actually just the way how we learn in math. Like every single detail that we learn in this one day right here is closely connected to information from the other days that we've learned. And I want you guys to think carefully. Can you take sine inverse of a 2? Go ahead. Make your choice. You can use a unit circle or use a. Actually, it's better that you run through the calculator and see what it gives you, what the calculator is telling you, and then maybe you can also try. This should happen pretty quickly. So cosine inverse of a negative 1.5 or something like that, right? Okay. Plus 1. Undefined. Some calculator say undefined, some calculator will say syntax error, some calculation will say error quits, right? But basically, yes, it's undefined. What about this one? Set it undefined. Okay, so we found those answers because the calculator said so. Now we are the human being, we know better than the calculator. Why did the calculator tell us that? So hypothetically, if we had an answer theta, right? You got to remind yourself again. Hypothetically, if we had an answer theta, then that means this thing here, sine inverse of 2, that equals some hypothetical theta right here. It means the same, right? The double-headed arrow, means the same as taking sine of theta will equal 2. Okay? What's wrong with this? What's wrong with sine of theta equals 2? That, right? Sine has to be just anywhere. The sine value can only be anywhere from -1 to 1. That's why this equation here is impossible to solve, right? See what I mean? Okay. And so that's the reason why taking sine inverse of a number bigger than 1 or less than -1 like that is impossible. And so now we put in another understanding right here for us. So yes, when you take sine inverse, right, of a value k right here to come out with theta, then yes, that means the theta come out will happen only anywhere from -5/2 to 5/2. But that's the outcome, that's the output. Now we're talking about if you want to, in order for sine inverse to run properly, right, on your number must be provided. Your number k it must be anywhere from -1 to 1. And so that is the same way with cosine inverse. Yeah. The cosine inverse operation. When you apply cosine inverse, right, on a given number, yes, tentatively we want to come out with an angle, some angle, and the requirement, the restriction for the angle that come out is anywhere from 0 to pi. Okay? But that's we're talking about the outcome of the operation here. But now, in order for the operation to work properly, right, you can only use the angle. I mean the value k that's anywhere from -1 to 1 as well. We did that experiment right there, right? In front of us. Yeah. Cosine of the -1.5 is going to be an undefined. That gets into with some actual problems. Set you guys into some good routine. Number 1. Number 2. Now when we're looking at the cosine inverse, this is just thought process. So there's not really anything to write down. Think about what theta, right? What theta satisfy? What angle theta satisfies a cosine of theta equals pi over 2. I mean square root of 2 over 2. That's what we're trying to answer with that. Okay. And so for an easy problem like this, we can go ahead and look it up on the unit circle as well. Right? Got a pi over 4. Any other one? So if we just simply solve an equation, right? Yes, there are technically 2 answers that come out. There are pi over 4 and there's 7 pi over 4 that give the cosine being the square root of 2 over 2. Now remember that cosine inverse only give out answers within anywhere from 0, right? 0 to pi or there. That's why this is the only answer that we can choose. All right, very good. So in that way right here, let's look at part B. So let's get for ourselves into a good habit here that anytime you recognize, so the business we're doing now is all about getting trig inverse function. Right? We're learning to calculate the trig inverse value. But then if the value in here is recognized from a unit circle, then use a unit circle to get an exact final answer. Unless you're having some unrecognized value that's some value that you didn't recognize from the unit circle, then you're going to use a calculator. See what I mean? Okay. So let's now look at sine inverse of how about a negative square root of 3 over 2. Once again, in the thought process, we don't need to write down anything like that, but keep in mind that we ask ourselves this question: what angle theta, right, satisfies sine of theta equals negative square root of 3 over 2. See what I'm saying now? If we want to look for that angle theta, but keep in mind now that for inverse sine, when we're formally doing the inverse operation, inverse sine operation, then the angle will come out right here. We only want the angle anywhere from minus pi over 2 to pi over 2. That is a restriction. Okay. You know what I mean? We only want the answer to fall inside of this interval. Right? So I'm writing this down right here. It's just to show you the thought process, but really for these kind of problems, there is not really anything to write down as a stat, right? As the written stat there. So it's just to get to know these things. Right? So you can see easily that on the unit circle as an explanation here, right? On the unit circle, now sine being negative means we're looking at the bottom side right here, right? Being negative square 3 over 2 again. So we've got two values. Negative square 3 over 2 is about that. So that's about a 4 pi over 3, right? That's one of them. Right? And then there's a 5 pi over 3 right here. Right? 5 pi over 3. But then that's if we go in a positive direction, right? Then if we were writing it like that, then these both fails the requirements, right? So we have to do a little bit of in our mind calculation right here, but think of that one right here as it's co-terminal with a negative pi over 3 angle. See what I mean? And then that one is co-terminal with a negative. This is the negative 2 pi over 3. But sadly, the negative 2 pi over 3 is out of that range again, right? And so of course, remember your picture here is on the unit circle. We want the output for sine inverse. We want the angle theta to come out only on the right-hand side. So it looks like this guy is the only candidate that passes, right? Now the answer here is a minus pi over 3. Good. So everything I'm writing down here is just an interpretation right here, but it's not really written separate here. So even when later on you guys get to your assignments, they're not really anything about these kind of problems you ask for as written steps. The written step is safe for other work. Similar, very similar, fundamental. When you are calculating, when you're applying an inverse trig operation, right? Let's set yourself into a good routine that if these values come out recognized from the unit circle, and use the unit circle to come out with exact expression like that. Okay. Unless you have, and it's gonna come right now. So think about sine inverse of a 0.85 or something like that, right? This is nowhere found, or it's not recognized easily from the unit circle. That's where you use your calculator right there. And now for these right here, I use my angles right here in radians. Let me go back. Let's put in an additional comment here, an additional instruction here. How about we want to evaluate it in radians? We need to use a pi unit right there. In radians. The reason I mention this now is because I remember in an earlier lecture I asked you guys to turn your calculator in reading mode, right? So make sure you turn it back. Make sure you keep your calculator now in radians mode. And then let's go ahead and apply the sine inverse of that 0.85. This time right here, I very much expect that the answer is going to come out like a pretty nasty decimal, right? But that has to be the way it is. Okay. 1.016. Does everybody else agree with that? Yes, it makes sense. Because think about it. This value is near closing up with the square root 3 over 2 like that, right? So this, the pi over 3 exactly is a 60 degrees, right? Either a positive or negative. Yeah, so this thing right here is 1.06. Pi itself is 3.15, so divided by 3 is a 1 point something, right? So these are closed, okay? And that's how I expected it, and that's consistent with 58.21 degrees UAE. Okay, but that's in radians. Sadly, with a problem like that, we gotta use the calculator. Okay? So once again, coming back to that, okay? Part G here. Let's look at about cosine inverse of a point 35. So once again, giving your answers in radians preferably. One, three, okay, 1.213 radians. Okay. Okay. All right, so example one was just to let you guys get comfortable with evaluating using the inverse trig function. And again, as I mentioned, when you can, right, look for those values from the unit circle and use the unit circle to come out with the exact answer that we more preferred. Right? And then when you can't, like say 0.35, when you can't find that value from the unit circle like that, right, then you gotta use a calculator. Right? So we still want to evaluate, but I want to bring in some special problem here so that after this example, we are going to be able to find out some special rules about it. But how about I don't need you guys to obtain an answer or anything like that yet. Let's see if you understand what I'm asking here. How about sine inverse of a 0.35, right? And then whatever answer that is sine. Right? So let's fire up a computational problem like that, evaluating problem like that. The order of the work here is that first, we're working from the inside out here. First, we apply the sine inverse operation on that number. See what I'm saying? Huh? And whatever outcome we have, then we apply the sine value of that. So, taking sine inverse of 0.35 is going to give me an angle. We come out with angle, and then taking sine value of that angle is just as usual, right? And then when things go nasty, we use a calculator. See what I mean? And then keep things gradient. And so now here's the thing. So go ahead. After I explain that the thought process, okay, then what would you do first? You punch it in the calculator, right? Get sine inverse of 0.35. See what I'm saying? No? Okay. All that the calculator gave, right? Right. So this is the outcome from taking sine inverse of this value. We're good with that, yeah? But now we're seeing this as an angle in some radians unit. Okay? Now we want to take the sine value of that. See what I mean? What's your final outcome? You guys come out 0.35, right? You guys all do that, okay? So right now we're setting that foundation by doing just the work we get from the inside out, right? And we get those angles and gradients together. So it may look a little bit close between these two numbers, the 0.35 and the 0.3575, something like that. It may look a little close, but they're completely two different things. 0.35 is a sine value, whereas this lengthy value here is an angle ingredient. You guys good with me on that still? Okay. So now, but then the answer that we have recognized all of a sudden, the answer is something, we didn't go too far into this kind of problem yet, but the answer here seems to be exactly the same as that original number that we've had, okay, right? And I wanted you guys to do the work and we recognize the idea of that. So, similarly, let's come up with something else here. How about we had cosine inverse. And you see the way how I'm writing it. I write that's it, from the inside out. I'm taking cosine inverse of a 55, right? And then whatever angle that is as an outcome, let's calculate cosine. Okay, so that was part A, so now we're firing up part B with that. So just do the usual work. Feel free to use a calculator. Okay, so now that is some angle ingredient, right? Think about we take cosine of that. 0.55, right? Of course, maybe the calculator rounded here a little bit, so that's why it may be a little slightly off here, right? Very slightly off. Okay? But the idea tentatively is that it's going to land exactly into that number at the beginning. Okay? Okay, so what have we drawn now is some two, and then maybe I'm going to come back and add in some more problems to that. But let's write down some generality here. Think about it. What we have recognized is that anytime we're taking sine inverse of a value, right? Like the sine inverse of 0.35 that we've seen in the example right there, and then after that, right, we take the sine value of that. The answer comes out being exactly what? Exactly x. You know what I mean? Okay. We did that through investigation right there. And so it's easy to understand. The reason for that is, think about it, this sine inverse, right? Sine inverse of x takes you to some angle, theta. See what I'm saying, no? That's the explanation for that sine inverse of x. Takes you some angle theta right there. And from the definition yesterday, from the definition we explained yesterday, sine inverse of x, go to some angle theta, it means the same, right? It means sine of theta equals x. See what I'm saying, no? It means the same as sine of theta equals x, and so that's why, thinking about, see, this is theta right here, some theta. So sine of theta is also the same as sine inverse of x. And that's why it came out being just x. That's the explanation for that. Yeah. Right. And so, after all of that explanation, so we wrote down a little rule right here that we recognize, right? Sine inverse of x, right, will equal exactly x. And this is always true. This is true for all x values anywhere from -1 to 1. Now, keep in mind one thing, that in the end, the operation on the left-hand side here works from the inside out. So in order to have the sine inverse successfully done, right, or in order to have sine inverse operation here successfully calculated, you got to have x restricted anywhere from -1 to 1, right? I pointed out that example in the earlier part of the lecture that we can't, do a sine inverse or a cosine inverse of a number like 2 or -2 or something like that, right? And so now similarly, we have found, if we're taking cosine of a cosine inverse of x, the answer would come out also exactly x, right there from our example. Right? Then provided that x that we work with in the problem has to be a value that's anywhere from -1 to 1. And then leave me some space between those two lines, because I'm going to come back and fill in some more lines of information. And now we'll go here, and I'm going to bring in a third problem. So what about, you guys take for me sine of a pi over 12? Okay, we didn't even have pi over 12 from our problem. And then from there we take sine inverse pi over 12. Remember the thought process here in our thinking, in the way how we're thinking, we go from the inside out. This time, see, the order of these things got switched right there. So first we have to calculate sine of that angle pi over 12. Okay. Sine of the angle, come out with some sine value, right? And then we take the inverse. Let's see what kind of answer we're ending up to. Right, 1.9. Right. So now we go ahead and run the sine inverse for that. See what kind of answer we have. 8. Okay. Well, it's a little hard to recognize, but if you do a pi over 12 right there, right? 3.14 divided by 12, or you get that value right there. Yeah, that's the part being a little tricky about these radians. Radians can sometimes be expressed in exact value and sometimes be expressed in decimal, right? Or it is exactly the same. Okay. So my point is that we're ending up with exactly a pi over 12, which was that answer that came out originally in that hard problem, right? That way in the beginning problem. Okay. And so now at this point again, that should have been problem C of our example. So in the next one right here, so cosine of the angle 1.35, right? It's not degrees, it's in radians. Okay? And then we take cosine inverse. Okay. I leave that for you guys to completely explore that all the way from the beginning to the end. Remember, we go from the inside out, right? We get cosine of 1.35 first. That's 1.35. Process is we took cosine of 1.35 first, and then we apply cosine inverse on top of that. So the process we recognize here, it goes the opposite way. The process we do here goes the opposite way in problem C that we've done throughout that example. Right? What we did is we took sine value of some angle theta, okay, and then after that we go sine inverse. It comes out exactly as we explored in our example, right? Later. And for this time right here, there's not even a restriction because the angle theta can be just anything, right? It can be any value right there, negative, positive angle. We take the sine value and then we take the sine inverse. Okay? And then similarly, cosine, right? We take cosine of some value theta, supposedly some angle, and then from there we take the cosine inverse, right? And then we explore throughout our problem, and the answer comes out exactly the same. Okay? So with these right here, we famously refer to them as the round trip properties. Okay. See, on the cosine, taking cosine of cosine inverse gives you the exact number, or the other way around. Taking cosine inverse of the cosine gives you exact value right there. That's why the two properties here together is one round trip property on cosine. Okay. One round trip property for cosine. And the same right here, this is the round trip property for sine right there. See what I mean? Okay. So, yes? Okay, textbook authors refer to this as the round trip. It's kind of going one way and go the other way back. Okay. Round trip properties. Right? That's how we call those. Okay. So from now on, after we have already learned and understood the round trip property, if I'm asking you, hey, cosine of a cosine inverse, right, of a 0.35 or 0.45, for example, right? And your answer should come out immediately, just 0.45 without any need to think with that. And so now, whoever that was, which words might hear that? It's canceling out. The idea is similar to canceling out. So yes, you may be allowed to think about that as canceling out, but be aware it's canceling out in the sort of like the opposite way, I guess, right? It's not like the multiplication is canceling out factors. You know what I mean? Because over time, I keep having students having this idea in mind. I keep having students having this thinking, cosine inverse, 0.35. Somebody in my class before mistaking that this is the same as a 1 over cosine of 0.35. See what I'm saying? And then having the other cosine outside of that, right? They think it out. They put the cosine on top of that, right? And they cancel out. That's very dangerous. Okay? So be careful with that. This is not the right way of thinking, even though you are allowed to quite often enough to think of that as the two operations here, right? They reverse each other out. That's why they cancel. They cancel in a way that they reverse each other out. Okay? They undo one. The cosine outside, they undo the cosine inverse. And then the same way, the cosine inverse, right? Undo the cosine. But they don't cancel out in the usual multiplication way. Multiplicative way. Sounds good? But so now the problems will become more challenging. Because we don't always just, work and beat around the bush with those kind of things like that. So now I'm going to introduce an example. And then along the way, we're also going to pick up a new idea right here. So example 3 here brings in one kind of special problem that quite commonly happen out there. And so we want to evaluate. Okay? Evaluate in, but I want you to, let's evaluate in exact expression. Okay? Exact expression. I'll give you a sine inverse of a 2/3 there, okay? And it's all proper, right? 2/3 is a number in anywhere from is a number in between -1 and 1, right? So it's completely possible and it's completely proper, right, to calculate sine inverse in 2/3. But now think about it, the process, once again, once we're done calculating sine inverse, we want to calculate cosine after that. Right? So it's not directly the round trip property. And the round trip property, you're gonna put a sine here to undo the sine inverse, right? But now it's not. See what I mean? We calculate sine inverse first, right? And then we whatever that is, we get the cosine value. See what I mean? Right? And so when we are introduced to this problem, I'm just like anybody else when I was first introduced to a problem like this, I would just rush into my calculator, get sine inverse in 2/3, right? And then do the work again, and whatever that comes out, I'm gonna punch that through the cosine operation again, and then gets nasty value again. See what I mean? Right? But then going in that way, I was completely off the hook. Actually, it was completely off direction because the instruction is making it clear we want the exact expression instead of just the decimals like whatever the calculator gave. I mean, you guys can try it. Go ahead and take sine inverse with 2/3 again. Do the calculation with your calculator. Sine inverse of 2/3. So it starts out with exact expression 2/3 as a fraction, right? And then we run the sine inverse on that. And then after you get sine inverse, we're gonna take cosine of that, or whatever that value that is. And you guys can go in radians, in whatever, radians or degrees or whatever your favorite choice is. Such a lengthy expression, and that's not the goal here anymore. We want the answer like that, the exact expression. So what exact expression? We have some decimal like this. So here's the plan, and this is like real written step right here. So I'm gonna scratch it somewhere that the answer was √5/3, or in decimals there was a point. Right? So decimals or exact expression that we already had some tentative goal, but the plan of working with this is like this. Keep in mind, sine inverse will always come out in some angle. You guys follow me right there? Okay? That's one thing to keep in mind. So now I'm going to erase that extra note. But before we writing that, yes, we're going to just simply let that inner work there, that sine inverse of 2/3, whatever that is, it's going to come out in some theta. You guys agree with me on that? It's going to be some angle, right? Well, let's assume that theta is a big time notation for angle. So sine is inverse of 2/3 will come out in some angle. And keep in mind now that this angle right here is somewhere in the interval because it's sine inverse, right? So from what we learned previously, this angle has to be anywhere restricted inside the interval from -5/2 to 5/2, assuming that I'm going in radians, most commonly. You guys get caught up to this point so far? So, remember from the definition I wrote on the board yesterday, on the board in the earlier lecture right there, sine inverse of whatever number equals an angle, it means the same. So logically, this statement here, sine inverse of 2/3 equals theta. It means the same that sine of theta, right, will equal 2/3. You agree with me on that? Right? This is what we wrote down from. That's my curve there. So sine inverse, right, of a value to equal theta means the same. The phrase if and only if it's another way of saying it. It means the same that sine of theta must equal k, the value inside of our inverse sine operation. See what I mean? So I'm using this exact definition and I'm putting it in to our problem there. All right, so we can keep it there for a little while. And that's why sine inverse of 2/3 equals theta. Once we let it like that, it means the same as sine of theta equals 2/3. Are we good with that then? Now, you guys, so that's sort of like one first step in the generality right there. We left our inverse part inside right here, right, to equal an angle theta. And then we kind of push that around a little bit, right? Now, the next target here is you get the cosine, right? Cosine of theta. See what I mean? You get cosine of theta. So, do we have an identity? Do we have an identity that relates between sine and cosine? Because in the end, if we let this to be cosine, if we let this sine inverse of 2/3 to be a theta, that means the whole expression here is also the same as cosine of some theta, right? Right now we know sine theta equals 2/3. we're on our way to find cosine of theta. See what I mean? Okay. That's the whole ultimate goal about this problem. Yeah. Right? And so, let me remind you guys, sine squared of theta plus cosine squared of theta, doesn't matter what angle theta is, must always equal what? 1. Sine squared plus cosine squared must always equals 1. And so what I did here is I used some trig, some known trig identity that we've learned previously that relates between what we have currently found, sine of theta equals the given value right here, and then we're relating that with our ultimate goal, cosine of theta. See what I mean? Right. And so now, sine squared of theta equals 2/3. So that means sine squared of theta is 2/3 all squared. Right? And then plus, and then we have the unknown cosine squared of theta equals 1. Right? And so 2/3 can easily be calculated that it's going to be a 4/9, right? So in other words, we've got 4/9 plus cosine squared of theta equals 1. So now from here, remember, our goal is to find out cosine of theta, right? We're almost there. Right? The problem turns into just finding cosine of theta. And so I'm going to subtract 4/9 from both sides, making it, so we subtract 4/9 from both sides. That's making it cosine squared of theta equals 1 minus 4/9, right? And you can make common denominator, making that the 9 minus 4 here, making it 5/9. See that there? We're getting there. So right as of this point, I'm looking at cosine squared of theta equals 5/9. So how do we go from cosine squared of theta to 5/9 again? Recall that the cosine squared means cosine of theta, right? And then all squared, right? So we're right around the corner to victory with that. We're looking for cosine of theta. What we have now is cosine of theta all squared. Okay. So how do we get to that? So to what we desire? It's just a matter of taking the square root both sides, right? So cosine of theta turns out to be taking the square root of 5/9. You guys follow with me on that, okay? But here's the problem. The real mathematical behind that is anytime we're taking a square root on both sides of our equation, what's the problem? What's the major thing? Plus and minus. Anytime we're taking the square root on both sides, you guys have made this far in math. Okay? Keep that nailed down in your understanding in math. Okay? Anytime we're taking square root on both sides of the equation, right, we run into a plus and minus. See what I mean? So, truthfully speaking, cosine theta can equal to 2 separate outcomes. And by the way, yes, these 2 outcomes right here, after reducing the roots, it's plus and minus square root 5/3. So yes, it seems like we're getting close to that answer that we got tentatively earlier, right? But how do we choose? How is it that we chose this positive one? Or how do we choose the answer from here? So now keep in mind, theta got to be an angle, because remember theta came out from being the sine inverse of 2/3, right? So theta is already restricted right beforehand here in that interval of minus 5/2 to 5/2. So if theta, think about on the unit circle, if theta is anywhere from minus 5/2 to 5/2, basically theta is anywhere on the right-hand side of the unit circle, right? Quadrant 1 or quadrant 4, you guys follow it? So that means anywhere in here, either you're down here or either you're up here, your cosine value has to be what? Positive. See right now? Okay. That's why we're ruling out this, we take the positive one. Right? So for that reason, I have to erase this space right here. We have chosen cosine theta equals 5/3. Right? We have found our answer, or more formally speaking, that exact expression, cosine of sine inverse of 2/3, right? That equals a positive 5/3 in exact expression. That's what I'm talking about. Okay? So it's not just about we use a calculator to run and get an answer. There are a lot of work into that. See what I mean? Did you guys see a generality out of this problem so far? I mean, it's got a few famous stages. I got to call it stages or steps. The big step. the first step is to start out with the idea of this whole problem is we're starting out with an inverse function, an inverse trig function from inside. Okay, and then from that, we're gonna come out with some angle, and then we're calculating a trig value out of that. It could be a tangent out there, it could be a sine out there, whatever else out there. And so the first thing is we're gonna do this, right? We're gonna let the inverse to come out with an angle theta. See what I mean? Okay, and then we switch that around to turn that into a trig equation, kind of like that. And then make sure to indicate properly the angle, the destination for your angle, right? Because this is giving some useful quadrant information. This sort of like gives a quadrant information. Right? And then this whole big stage right here, right? The idea is we must use some trig identity. So here, there's no guarantee that it's always going to be this trig identity, but we're going to have to use some trig identity to find out the unknown other trig function that we're looking for. See what I mean? And then we use and then right from here, a lot of times you're going to have to run into two answers. We use the quadrant information to roll it down, right? The right choice of the answer for us. All right.